Okay, welcome to Math 310, Introduction to Modern Algebra. So this is lecture 15, sorry. We're going to be continuing to work on rings. If you haven't grabbed your homework or exams or solution keys, please feel free to grab those after class. And so what I wanted to do today was start with a problem which may not seem too much related to what we're doing, but there is a nice connection. And I know a lot of you are going to be, considering careers as teachers. You want to try to find ways to make the math that the students are doing interesting and relatable. If you really want to kill someone's love of math, have them do 40 quadratic polynomials, finding the roots, and they will learn the quadratic formula, but they will not have any sense of why you want to do something like this. So this is one of my favorite riddles. So you have an army with 10 generals. You want a security system so that any 3 generals can launch the nuclear missiles, but no 2 can. So you have to give information in such a way that any 3 know the password, but no 2 know it. And so the password is going to be a triple ABC. It's going to be the coefficients of a degree 2 polynomial, a nice quadratic. So the question is, what information should be given to the generals so that any 3 of them can find out ABC, but no 2 of them can? So what's the simplest information you might think of giving generals? It may not work, but what's the simplest information you might think of giving a general? What could you give them? A, B, and C. So try giving generals some of A, B, and C. Try giving each general a subset of ABC. So is it possible one general gets all 3? So case 1, a general gets all 3. Could launch, thus cannot do. So do we all agree we can't give a general all 3 of A, B, C? All right, what's case 2? So case 1 is the general gets all A, B, and C. What should case 2 be? Yeah.
The general gets like 2 of them.
Good, the general gets 2 of them. So a general gets 2 without loss of generality, say A and B, because we can always just change the labels. Is it possible that this could work? Maybe everybody gets 2 pieces of information. Some people get 2 and some people get 1. Remember, any 3 generals have to be able to launch, but no 2 generals can launch. So if one general has A and B, what could be the potential issue? I'm sorry? What do you mean by only 2 generals have the codes?
One is A and B and the other is C.
Okay, if somebody knows C, then the 2 of them could launch. So nobody can know C, which means we won't be able to launch. So if someone knows C, the 2 can launch. Thus cannot do. So we got a contradiction if one general knows all 3. We got a contradiction if a general knows 2. What's the only case left? Each general knows 1. Case 1. Case 3. Each general knows only 1. Why is that bad? Yeah.
You have to guarantee that 3 generals you picked had the 3 different things.
Okay. So maybe general 1 gets A, 2 gets B, 3 gets C, and 4 gets without loss of generally A. And now 1, 2, and 4 cannot launch. So if you only give the generals one piece of information of A, B, and C, without loss of generality, we might as well assume the first general gets A, the second gets B, the third gets C. This is great ways to write the arguments cleanly. And now when we get to 4, it doesn't really matter what we give 4. We're going to have a problem. So unfortunately, looking at this, it seems like this is impossible. The reason it seems like it's impossible is it is impossible if this is how we do things. So if we're giving the generals information by giving them 1 of A, B, or C, or 2 of A, B, or C, or 3 of A, B, and C, there's no way we can satisfy these constraints. So we have to do something else. It's very important to remember, what are we trying to do? We are trying to set it up so that any 3 generals can figure out what A, B, and C are. We're not trying to give the generals A, B, and C. We may choose to do that. There may be a good way to get to the point where any 3 of them can figure out A, B, and C, but that's not what we're trying to do. We're trying to set up a situation where the generals have some information and they can come together and they can use that information to get A, B, and C. So we just figured out giving the generals a subset of A, B, and C is a bad idea. What else could we try to give? So we have, f of x equals ax squared plus bx plus c, giving A, B, or C doesn't work. So any thoughts about what information we might give the different generals? What should we give general 1? Any thoughts of what information we could give general 1?
Value for x to the quadratic roots.
Okay, so what value should we give general 1? Treat me like,
Zero?
I'm sorry,
0?
what do you mean by 0?
I'm thinking if that quadratic has a solution for x, maybe gives the solutions.
Okay, so but that's gonna have at most 2 solutions. Could have a repeated root.
Yeah.
So you're saying find the values of x that make this equal to 0.
You could. I don't know where that would lead you, but
That's one thing you could do, is you could say, I'm going to give you the x coordinates, and then I want to get from the x coordinates to the A, B, and C somehow by teaming up with other generals. You're on the right track. You want to give some information related to the polynomial. What might be a good thing to give to general 1? You've got this polynomial ax squared plus bx plus c. What could you give to general 1? Yeah. I'm sorry? Well, x is a variable, right? So you can't give them ax squared. That's really saying I'm just giving them x. I'm giving them a. If I give you a polynomial, what can you do to the polynomial?
plug in 1 for x.
You could plug in something for x. But what should you give them? F of 1. What should we give general 2? F of 2. And now we have n points. So the information of the points, 1 f of 1, two f of two, dot, 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 n f of n. How many points determine a line? Two points, right? Unless you're in marketing, and 1 point determines a line. You just need to know what your boss wants to say. So 2 points uniquely determine a line. Three points, a parabola. 4 points, a cubic. So if I give you this, if I gave you 2 points, could you find the equation of the line going through 2 points? Yeah, you've got 3 different ways, I think, of doing that from algebra. So now, if I give you a couple of points, let's say, this point, and this point, maybe we can figure out, what is the parabola that goes through this? And so we would have, if we call these points, maybe I'll call it x1, x2, x3, you'd get a x1 squared plus b x1 plus c equals y1, a x2 squared plus b x2 plus c equals y2, a x3 squared plus b x3 plus c equals y3, or a, b, c, x1 squared, x2 squared, x3 squared, x1, x2, x3, 1, 1, 1 equals y1, y2, y3. Can you solve for a, b, and c? So what do you think? Are we going to be able to find a, b, and c? We have 3 equations and 3 unknowns. Do you expect to be able to find a, b, and c? What must be true if we want to find a, b, and c? So if we want to be able to find a unique a, b, and c, what must be true about this matrix? So linear algebra is a prerequisite for this class, right? We're solving a system of equations. If I want to solve the system of equations, what must be true about this matrix? Please don't make me call up your linear algebra professors. Can you always find a solution if I give you ax equals b? Does every equation like this have a solution? So no matter what I give you, let's go back to 2 dimensions. If I give you alpha, beta, gamma, delta, x1, x2 equals y1, y2. Oh, I guess we're doing b, so I'll do b1, b2. We're trying to solve ax equals b. Is this always solvable? So that's basically saying 2 lines always intersect. The first one, alpha x1 plus beta x2 equals b1, alpha, gamma x1 plus beta, no, delta x2 equals b2. This is saying no matter what 2 lines I give you, they intersect. Do every pair of lines intersect? When do they not intersect? When they're parallel. How can you tell if 2 lines are parallel? What's true about the matrix? So it doesn't always have a solution. So no solution if the lines are parallel. Or how do you tell if I give you a matrix equation like this if there's no solution? Did you solve systems of equations in linear algebra? There's a nice number you can associate to a matrix. What's that number?
Value?
A matrix would have more than one eigenvalue. But the thing I'm thinking about is the product of the eigenvalues. The challenge, no solution if lines are parallel. If the determinant is 0, might have no solution. If I give you, for example, 1, 2, 2, 4, x1, x2 equals 3, 6. What's the determinant? So what would be the determinant of the 2 by 2 matrix?
0.
0. Is there a solution? So is there a solution? The first line gives us, 1x1 plus 2x2 equals 3. The second is 2x1 plus 4x2 equals 6. Do these two lines intersect? How do I get from the first to the second?
Multiply the whole equation by 2.
It's the same line. Do the two lines intersect? Yeah, there's infinitely many solutions. It's the same line. So just because the determinant is 0 doesn't mean there's no solutions. It just means we can't invert the matrix. We can't write, if we have AX equals B, we can't write X equals A inverse B. We'd love to solve, we want to say X is A inverse B. So if the matrix is invertible, then you can always solve and you can find. So over here, the question is, will this matrix be invertible? No matter what I choose for x1, x2, and x3, will this be invertible? And so as a nice extra credit, show that it is invertible as long as x1, x2, and x3 are distinct. So it is invertible if x1, x2, x3 are distinct. Yeah. In chapter 3, they talk about the evaluation homomorphism, where you take a polynomial, you evaluate it at a point. That's what we're doing here. We're evaluating. So I'm trying to give you an application of why you might care about some of the stuff we're seeing in the chapter. This is also, a really great interpolation problem. If I have a couple of points, can I figure out what curve goes through them? If you give me 7 points, I can find a polynomial of degree 6 that goes through them. Almost surely. If you give me, 6 points that are vertical, okay, with, that's not, but as long as you give me, reasonable points, I can find a polynomial. It's not that impressive. If you give me 101 points, I can find a polynomial of degree 100 that goes through it. It's not that impressive. If I find a polynomial of degree 5 that goes through your 101 points, that's impressive now, because I don't have that many free parameters. If I only have 6 free parameters and it's going through perfectly 101 points, something must be going on. There must be a real relationship. And so over here, 3 points will uniquely determine a parabola. As long as the points have different x coordinates, I can always do this. What's nice about this is you could make some generals more important than others. How could you make general 1 more important? What could you do? Any thoughts? Yeah, it's still just 1 point though. Now, if they knew that it was the vertex and if they knew that the polynomial was symmetric. So you need to do it a little more. So making some more important. Let's say need 10 to launch. So if we need 10 to launch, we now have a polynomial, a9 x to the 9th plus ... plus a1x plus a0. So we want the tuple a0, a1 all the way up to a9. If you knew the polynomial was symmetric, well, let's say you know the vertex. And again, I'm not going to draw a general degree 9 polynomial, but let's say we have something like this. If you have the vertex and if you have some degree of symmetry, then as soon as you have one general who gives you this point, you would actually have the corresponding point over there as well. So if we had a polynomial of degree 2, and you know the vertex, then as soon as you meet anybody else, they're actually giving you 2 points, not just 1. So that would be one way to do it. And that would allow you to have one person special. What if you want to have several people special to different levels? Maybe the president of Siena can launch by themselves. The provost needs at least 1 professor to join them. 3 deans might be sufficient. How could you give different strength to different people? So let's say you need 10 coefficients to launch. How could you make sure the president can launch by themselves? There's 2 ways to do it. How can you make sure the president can launch by themselves? Suggestion? Yeah, give them all 10 what? So you could give the president all 10 coefficients because they're doing anything they want by themselves. Or you could give the president 10 points. Or I guess maybe 11 points. Let's see. No, right. Give them 10 points. Give them 10 points. What if you want a dean? What if you want the provost to be able to launch with just 1 professor? What could you do? So before we gave every professor 1 point, how could you make the dean more powerful than the provost more powerful than a professor? So 10 professors can launch because 10 professors could figure things out. So what information should you give the provost? So the provost only needs 1 professor. Yeah, give the president 10 points. Give, say, provost 9 points. Maybe give deans 4 points. So 3 deans could launch. Anybody know how many deans Siena has? There's a great email called Administratium about how certain organizations tend to become administratively heavy over time. Let's say we have 8 deans. Okay. And let's assume 2 are married. Do you want those two deans to be able to launch with a third dean? Or is that giving you, so you're concerned that that's giving maybe too much power to one family? What could you do?
It's the same.
You give them the same points, so maybe the couple gets same points, or maybe 3 of 4 the same, something like that. And you could be you're concerned about clicks. So what you could do is you might say, I might give you some of the same points as someone else, so that you need to have at least so many other people involved. There's lots of things you can do with this. And so what's important about a problem like this is your objective is to get to the triple ABC. It's how do you provide information in such a way that you can get there? And it comes down to, can we recover a polynomial from knowing the points? This is Lagrange interpolation, which you might have seen. This is one of the biggest problems. How do I recover? How do I try to figure out what the functional form is? We're using the polynomial evaluation now. I will give you a problem to think about for next time. This is one of the many hat riddles. So you have 100 hats. Each is white or black. The people are in a line. Person K sees 1, 2, ... K minus 1, and no one else. Has anybody seen this one yet? One, 2, 99, and 100. Okay. And then the hats are placed deliberately. So the 100 people are mathematicians. They strategize first. Evil prof hears conversation, chooses hat assignments, at time 1, person 100 speaks. 1 second later, person 2, then 1 second later, person 3, and so on and so on. You say either white or black. If correct, team gets let's say $1 million. If wrong, prof gets 1 million. How much can you ensure you get? Okay, so does everybody understand the problem? You've got 100 people in line. The last person sees everybody. The first person sees nobody. And you can only say white or black. If when you speak, you are correct, your team gets $1 million. If you're wrong, you owe the professor $1 million. And so you can come up with a strategy based on what you see. This is what you say. But I will know your strategy. And I will choose the hat assignments in such a way so that if anything can go wrong with your strategy, it will. What's the most you can guarantee that you will get? Okay, does everybody understand? So this is related to a nice concept that we have seen in this class in terms of how to solve something like this. Yes? You are saying white or black. So if you speak and if you're wearing a white hat and you say white, your team gets $1 million. If you say black and you're wearing a black hat, your team gets $1 million. If you say white and you're wearing a black hat, I get $1 million. Everybody has to speak. And you speak in a specific order at a specific time. Otherwise, you could say, I'm going to wait a certain amount of time, because there's only 2 to the 99 possibilities of hat assignments in front of person 100. If I speak immediately, everybody is white. If I speak after 1/299th of a second, it's all white followed by a black. If I speak at, you're not allowed to use a delay to pass information. Okay?
They're like a preset amount of like each hat.
Nope, I'm evil. So whatever can go wrong, it will go wrong. If the worst thing for your strategy is for there to be 88 white hats, there will be 88 white hats. Can somebody give me a strategy that guarantees that you are at least indifferent to playing, that your team can get at least 50 hat colors correct? I'm sorry?
Oh, I know.
Yeah, because I'm evil, remember, evil. And so if I know everyone's going to say the same color, so as a general rule, before you do a hard problem, what should you always do? Easy, right? That's why we're doing this. Why would you study 100? What should you do first? Okay, so if there's just one person, because this is being recorded, I can't say exactly the technical term for the situation, but it begins with a letter that follows E and precedes G. I know your strategy. Is there any way person 1 has a chance? No. All right. What if there's 2 people? So person 2 speaks and then person 1 speaks. Any thoughts about what person 2 should say? To guarantee that at least half the people who speak are correct. Person 1 gets to hear what person 2 says. Yes.
Say the color.
Yeah. So say color of hat in front. And so if I know that that's what you're going to do, because I'm evil, what will I do? If I give person 1 a black hat, what will I do to person 2? I'll give a white hat. But you've just shown that if there's an even number of people, you can guarantee that at least 50% are correct. And then I can guarantee that the other 50% will be wrong. So then building on your success here, what comes next? What should you do next? So that's one possibility. One possibility is 3. Maybe this is what what's another possibility? Instead of doing 3 people next, we could do there might be a number that might be better than 3. Any thoughts? 4. So for some things, it's actually better to just be doubling. So it's not immediately clear, what do I want to do next? Has anybody taken probability in this class? Have you done convolutions? Oh, okay. Sometimes when you're looking at things, it's easier if you go up by powers of 2. And so it might be easier to go to 4. Or there might be an even versus an odd. There might be a parity issue. So it's not immediately clear, is it better to do 3 or 4? If it's not clear what you should do, try 3, see if that works. If it doesn't work, try 4. If 4 works, what should you do next? Maybe 8. Or maybe you do 3 and then go from 3 to 4 to 5. So there could be lots of ways of looking at it. But again, what I really care about is the thought process about how you attack problems like this. Start off with something simple. Don't do the original problem. Don't start off with trying to do 100. I was just talking with somebody about a summer research project that I'm going to work with them and some students on over the summer. And I fooled them and I had them starting to think about the very hard. No, you don't want to think about that. You want to think, oh yeah, you're right. We should be thinking about this one first. But no one wants to do that problem. You want to do the hard one. But you build intuition first. And then the question is, which is the right way to generalize? And if you're not sure, try doing it both ways. All right. So now turning back to more of the standard material. So let's go back to properties about rings. So we talked about what it means to be an integral domain. So an integral domain means you have no divisors of 0. So you can't have two numbers that are non-zero that multiply to 0. So can somebody give me an example of a ring that is not an integral domain, where you have two numbers that are not 0, but multiply to 0? This is one of our go-to examples. So I want a ring where you have two numbers that multiply to 0, and neither one of them is 0. What are your thoughts?
Clock multiplication.
Clock multiplication, how many hours? 12. And what's your example? 2 and 6, okay. So it's either 2 and 6 or 3 and 4, right? So this is a great example of two numbers that multiply to 0, but neither one is 0. We don't have this in standard arithmetic. So things can be a little bit different in rings. So the question is, which properties from the numbers that we're used to continue to hold? We'd love to have the cancellation property. If I have AB equals AC, then either B equals C or A equals 0. And the idea is, well, look, if A doesn't equal 0, let's just multiply by A inverse on both sides. But not every element is invertible. And so proposition 3.15 says if you have a commutative ring, it has the cancellation property if whenever AB equals AC, then B equals C or A equals 0. And conversely, if B equals C or A equals 0, then AB equals AC. Okay, if B equals C, is this really a difficult statement? That AB equals AC? If B equals C? If A equals 0, is it a difficult statement? Right? So if A equals 0, clearly this equation is true. If B equals C, clearly the equation is true. So it's not really a big deal. The big deal is that if AB equals AC, then that implies either A is 0 or B equals C. And it turns out that a commutative ring has this property, this cancellation property, if and only if it's an integral domain. So that means there's two things to do. Show that if it's an integral domain, then it has the cancellation property, and show that if it has the cancellation property, then it's an integral domain. So you get to assume one and then try to prove the other, and then you switch. So which would you like to do first? Assume that it's an integral domain, or assume that it has the cancellation property? Which should we try to do first? Not a hard question.
Right to left.
Right to left. So we're going to assume, we'll go in this direction. Assume R has the cancellation property. Show it is an integral domain. So there's a couple of ways we could go. One is we could try to do a direct proof and show that it is an integral domain. We could also do a proof by contradiction, assume that it's not an integral domain, and then get a contradiction. So to me, those are the two natural ways to attack something like this. My first thought is, if we assume that it's not an integral domain, that might be able to give me a good violation of the cancellation property. So let's do a proof by contradiction. Let's assume it is not an integral domain. So we have x and y with xy equals 0, but x and y are not 0. So we want to show that this can't be, that R can't have the cancellation property. And because we know we've assumed R has the cancellation property. So that means our assumption was wrong, so that it means it has to be an integral domain. So we have to find choices for A, B, and C. So what should we take for A? What should we take for B? What should we take for C? We know xy equals 0. And we want to show that the cancellation property fails. So we've got to figure out how to fill in the table. What should we try for A? What should we try for B? What should we try for C? And all we know is x times y equals 0, but x and y are both non-zero. So any thoughts for A, B, and C? And if you don't know what they should be, where should we at least choose what should be involved in coming up with the A, B, and C? So what should be part of the quantities A, B, and C? Where should they be coming from? What's the only thing we know right now?
Which direction are we going again?
We're assuming R has the cancellation property, and we're showing it as an integral domain. So we're going to do a proof by contradiction. So we're assuming it's not an integral domain. So that gave us two elements, x and y, whose product is 0, but neither one of them is 0. So the only thing we really know right now is x times y equals 0, and x and y are not 0. So what must be coming into play in determining A, B, and C? What quantities must somehow play a role in constructing A, constructing B, constructing C? What do we have to play with? Any thoughts? There's not that much on the paper. What's the only thing we have? Do you want to try it?
X1.
Nope. We have something in addition to x and y. We have x, y, and 0. So we have somehow three quantities. We have x, we have y, and we have 0. And these somehow have to go in. And it could be maybe it's x times y times maybe x squared, maybe y cubed. I don't know. It's got to be functions of x, y, and 0. So what are your thoughts? What might be a good thing to try for A? What might be a good thing to try for B? What might be a good thing to try for C? It's okay if it doesn't work, but you should at least have something to try. What would be a good thing to try for A? X. And for B?
Y.
Y. And C? 0. And so if we try that, then we would have A, B would be x times y is 0. AC would be x times 0 equals 0. Therefore, AB equals AC, but B does not equal C, and A does not equal 0. Contradicts R has the cancellation property. So this is similar to some of the results we proved in group theory before. We were trying to figure out what elements to use. How do you do the proof? It's trying to figure out, how do I use the givens? So, the hard part here is, do I want to do a proof by contradiction? Do I want to try to do a direct proof that if it has the cancellation property, there can't be divisors of 0? Either it would be easy to say, well, if I'm proving it by contradiction, then it's not an integral domain. So I now have these special points x and y that are non-zero but multiply to 0. And that gives me good things to play with. So I'll leave the other direction to you. So we did the direction of assume it has the cancellation property. We proved it has to be an integral domain. Now you can go in the other direction. Assume that it's an integral domain. Prove that it has the cancellation property. So I'll leave that as an exercise for you to do. But again, when you're looking at things, you really want to get a sense of what you have to play with. And so the equation we have is xy equals 0. That gives us 3 pieces of information. It gives us x, it gives us y, and it gives us 0. So we want to somehow figure out how to move in the x, y, and 0 into the a, b, and c. How many ways are there to put them in? Well, if each one gets something different, I've got 3 choices for A, 2 choices for B, and then C is forced. So if I have x, y, and 0, and I'm plugging them in here, and I don't have anything taking the same as anything else, there's only 6 things to try. That's not too bad. Unfortunately, maybe 2 of them are the same. Maybe something is x, y, and maybe something else is y squared. And as soon as you get that, then you could have infinitely many things to try. But we just need to find one counterexample. I don't need to find, all counterexamples. As soon as I find one, I'm done. And so the hope is maybe I can find one by doing something simple. And you start with the simplest thing you can. And if it works, great, you're done. If it doesn't work, then you think harder. But you want to automate the process as much as possible in terms of trying to figure out how do you attack problems like this. Okay. So the next one is, let R be a commutative ring. The group of units of R is denoted by R star. And as a Bostonian, this is a fun thing to say. It's defined as the set of all elements of R such that there's some B such that A times B equals 1. So these are the groups of units. These are the invertible elements. So the group law on R star is ring multiplication. We call the elements units. And so the proposition is that the set of units is a group with the group law being ring multiplication. And as always, we are assuming R is a commutative ring. I don't know if we explicitly assume that the multiplicative identity and the additive identity are different. If they're not different, if 1 is the same as 0, then what does the ring look like? So if 1 is the same as 0, what does the ring have to look like? So if 1 equals 0, then R is something really simple. It's just going to be 0, right? Because multiplying by 1 can't change you. But if 1 is the same as 0, multiplying by 0 gives you 0. So in the special case that 1 equals 0, the ring is just the 0 element. What's 0 times 0? But if 1 equals 0, what's 0 times 0? It's also 1. So in this special case, when 1 equals 0, then your ring has just one element, and everything is invertible. 0 is invertible. Right? As long as 1 is not equal to 0, then you don't have that absurdity. So sometimes you say, look, let's just look at a ring and we'll assume in the ring that 1 is not equal to 0. The ring has to have at least two distinct elements, the multiplicative identity and the additive identity. So let's, in proposition 3.17, we will have dispatched the case when 1 equals 0. So let's assume we are looking at a situation where 1 is not 0, and we want to show that it is a group under ring multiplication. So what's nice is this allows us to go back in time. I made some comments about your linear algebra instruction. Now we can make some comments about who taught you group theory. How well do you remember group theory? Hopefully well. What properties do we have to show so that it's a group? So what properties does a group have? How many?
4.
4. And they are
Associative. Closed.
closed, identity, and inverse. Okay, so is associativity clear? If we take 3 elements, so if we have U1, U2, U3, does that equal U1, U2, U3? So the proof is something we've seen many times. Why is that true? What do we know about R? R is a ring, which means it's associative. So it's inherited. So we assume because R is a ring, that multiplication is associative. So if you restrict yourself to a subset of R, it's still going to be associative. So that's not so bad. Identity. 1 is in R, 1 is in R star. So let's prove rigorously that 1 is in R star. Can you give me some number which if I multiply 1 by it, I get 1? Yeah, as 1 times 1 equals 1. Right. We technically have to prove that. Right. The definition is there is some B satisfying AB equals 1 that it has a multiplicative inverse. Okay, we have identity. Let's do closure or inverses. Let's do inverses first. If A is in R, is A inverse in R? Well, as A is in R, there exists a B such that AB equals 1. So B is A inverse. Right. This is how we denote, this is what it means to be an inverse. Should I also say that I need BA to equal 1? We need, BA equals 1, but as R is commutative, we get for free. So we now need to show A inverses in R. there's a C in R such that A inverse times C equals 1. What should we take C to be? So we need to show that A inverse is an R. To show A inverse is an R, there has to be some element in R such that A inverse times that element equals 1. What do you think we should multiply A inverse by to get 1? So what should I multiply A inverse by to get 1? A. Right? So if we just take C to be A, then we do, in fact, find that it is contained. So we have associativity, we have identity, we have inverse. The only thing left is closure. So proof continued. We have to show closure. So what does this mean? We have to show if A1 and A2 are in R star, then A1, A2 is in R star. So let's unwind. As soon as I tell you that A1 and A2 are in R star, what information does that give us? What do you know as soon as I tell you A1 is in R star? So as A1 is in R star, what do we know? Good. So we know its inverse is in R star, and we know that there's some element such that A1 times that element equals 1. That's what it means to be the inverse. So that implies there exists a B1 such that A1 B1 equals 1, B1 is A1 inverse. Similarly, because A2 is an R star, that implies there exists a B2 such that A2 B2 equals 1, B2 is A1 inverse. To prove A1 A2 is in R star, we must find a B12 such that A1 A2 times B12 is 1. So this is the method of divine inspiration. As long as I can write down a B12 that works, it doesn't matter how I got it. It's nice if there's a very mechanical procedure that I could then use to solve related problems, so that you can trust that you will be divinely inspired on a future problem. But any thoughts about what we should try for B12? I need something so that when I multiply A1, A2 on the right by B12, I get the identity. What should I try for B12? Any thoughts? Yes. B1 times B2. And that would be A1 inverse times A2 inverse. You have the wrong index here. So is that what you want to try? A1 inverse, A2 inverse? Okay, so if we try that, what would we get? So we would get then A1, A2, A1 inverse, A2 inverse. Now what do we do? It's commutative, so it's commutative. So this is the same as A1, A1 inverse, A2 inverse is the identity. So normally, instead of doing A1 inverse A2 inverse, you would normally do A2 inverse A1 inverse. It's just an easier way to write it because then the inverses just line up naturally. Doesn't matter because it's commutative. And so we found a B12 such that A1, A2, B12 equals 1. So A1, A2 is an R star. And that finishes the proof. So again, it comes down to, if I want to prove this, I know A1 and A2 are an R star. So what information can I extract from that? In the real world, who knows what a red herring is? What is a red herring? That's right, it's extra information. In the real world, almost surely you will either have red herrings that have nothing to do with the problem, or you will not have enough information to solve it. It is very unusual in the real world that you'll be given exactly what you need to solve the problem, nothing more, nothing less. In math textbooks, we're often not in the real world. We're often given exactly what we need. Now, as you take a more advanced math class, you might be able to find ways to do things with weaker assumptions. And it's what's the weakest assumption I need to get a certain result? But over here, if I'm telling you something, almost surely you're going to need to use that in the proof. And so if it's a commutative ring, do we need to use commutative here? Would this result be false if it was not commutative? Okay. So some needed results, that will help us understand the structure. And again, part of the reason for the order of the material is this allows me to review things you've seen before. So some of the stuff we're about to see, we have seen before. I know we've seen it before. I'm not senile. I also have the ability to actually look at the slides to see what we've done before. The more times you see material, the better. This is one of the reasons why the author has written the book as he has. And he actually has some comments that rather than doing all the groups, all the rings and whatnot, he likes to return to the material so you keep seeing things. So one of the needed results goes all the way back to chapter 1. If A and B are integers, not both 0, then you can find integers U and V such that AU plus BV equals the GCD of AB. So I think the only difference from this and what we've seen before is using U and V rather than X and Y. All right. What is this also known as? What famous name have we given this? Euclidean algorithm. And with the Euclidean algorithm, not only do we know, actually, it's more than just X and Y. They're also flipping the role. A and B is what we were calling X and Y, and U and V are what we were calling A and B. But not only are there such integers U and V, but we have a fast way of finding them. And then there's a link to a paper I wrote with one of my colleagues at Williams. It turns out that the following is really difficult to prove rigorously. If a prime divides a product, then it divides at least one of the factors. We've seen examples that this is not true when we look at generalizations of the integer. When we looked at the ring, Z adjoint the square root of -5, all numbers of the form integer plus integer times square root of -5, you could have the case where something divided the left, but it doesn't divide either factor on the right. So this ability to have division is really nice. So let me just quickly put this here. So give myself a little bit more space. So if P divides XY, then P divides X or P divides Y. What do you think might be a nice result to use to prove this result? What do you think might be helpful to prove that if a prime divides a product of integers, it divides at least one of them? This is the Chekhov-Gunn School of Mathematics. So can somebody remind the class, what is the Chekhov's gun rule? I don't think it has to be the same scene, but you should be fine. There's rules about, how long can you go before you introduce it. And there's often some interesting, rules in murder mysteries as to just how much information do you have to give so that the reader has a sporting chance of being able to solve the mystery. And so, you might just casually mention, the person is looking around the room and they say a bunch of things, including a gun, and then that gun is going to be fired later. But you should be planting the information that you're going to be using. And so in a math book, the math book is ordered along the page axis. So you're going through things, you're introducing material in a certain way. Almost surely the stuff that's being introduced is being introduced for a reason. Any thoughts about what we might want to use to prove if a prime divides a product, then it divides at least one of them? So look at this slide and apply Chekhov's gun. Yeah, the Euclidean algorithm, which is at the very top of the slide. Maybe that's why that's there. So if we want to apply the Euclidean algorithm, we have to figure out how to use it. So proof. We have P divides X and Y. Without loss of generality, let's assume P does not divide X. Show P divides Y. The reason is if P divides X, it's really not that hard for me to show that P divides X or Y. Yes? So let's assume P does not divide X, but P divides X times Y. I want to use the Euclidean algorithm. So if I'm going to use the Euclidean algorithm, I have to have two numbers that come into play. What do I want to apply the Euclidean algorithm to? What numbers should I use? There are three possibilities. What are the candidates? Who's in the running? How many inputs do I need for the Euclidean algorithm? How many numbers do I need for the Euclidean algorithm? 2. What are the only numbers I know about right now? I'm sorry?
A and B.
No. Right now. Sorry. Oops. No, that's not this one. Ooh. What's the only thing? What are the numbers I know? What numbers do I know? Almost. I know one other thing. I know X, I know Y, and P. I need two numbers from P, X, and Y. Maybe it's X cubed Y minus XP cubed. And if that's the case, Lord help us, right? We're not going to find something like that. If I've got X, Y, and P, if I'm lucky for the Euclidean algorithm, I have to choose how many of X, Y, and P. How many of them do I have to choose? 2 of X, Y, and P. Right? The Euclidean algorithm requires 2 inputs. The only thing I know right now is P divides X, Y. P does not divide X. I want to show P divides Y. So how many ways are there to choose 2 of X, Y, and P? Order doesn't matter, right? The Euclidean algorithm doesn't care about the order in which you do things. So how many ways are there to choose 2 of X, Y, and P? So somebody give me a way to choose 2 of X, Y, and P. Yes. X and Y. What else? I wouldn't do YP next. I would do, I've chosen X and then I've chosen Y. Next one, so I don't miss anything. XP. And what's the last one? YP. Those are the three choices. Right? So again, the whole point is to try to create a procedure that will help you get to the proof. Hopefully, at least one of them will be a good choice. If you choose something and it's not working well, what should you do?
Try the other.
Try the other one, right? And so any thoughts? Do you think you want to use xy, xp, or yp? And we know p divides xy, p does not divide x. Which pair do you want to use? X, Y, XP, or YP? You've got a 1 in 3 chance minimum if only one works. If 2 works, you have a 2 in 3 chance. If all 3 works, doesn't matter what you say. Yeah. YYP. Okay. Which are you more lucky about or feel better about, the Y or the P? The P. So do we all agree that we probably don't want to do X and Y? Now, if I choose Y and P, I would get, there exists A and B such that AY plus BP equals the GCD of YP. Do you know what the GCD of Y and P is? No. What if we chose X and P? Then you would get there exists A and B such that AX plus BP equals the GCD of X and P. And P doesn't divide X. What's the GCD of X and P? 1. So would you like to keep your choice of YP or would you like to switch to XP? You'll switch, yeah, because we know the GCD is 1. So let's continue there. So we have integers A and B with AX plus BY, I'm sorry, BP equals 1. We know P divides X and Y. Damn it, I don't have an X and Y in this equation. Is there any way I could get an X and Y in this equation? I have AX plus BY equals P. I know something that P divides XY. What could I do? I want to somehow use this. So I need to get an X and a Y together. How can I get an X and Y together? What could I do? So I've got AX, yes.
Could you write P develops X, Y as X, Y is P times some X, or P equals X, Y over some X?
So you want to say MP equals XY.
Yeah.
Okay. So this is the equation I have. I have AX plus BP equals 1. I want to somehow get an XY. How could I get an XY from this? So you could try to write MP equals XY, but I'm still, would you then solve for P? Would you solve for X? I could then say, P equals XY over M, and maybe substitute that in here. Maybe get AX plus B XY over M equals 1. But I'm not sure how I'm going to get a contradiction from this. It's not a bad thing to try. Can you think of something that divides the left-hand side? What's the only thing that divides the right-hand side? 1. Can you see anything that divides the left-hand side? Does it look like anything divides ax plus bxy over n? Does it look like something divides the left-hand side? It should look like something divides the left-hand side. What does it look like the left-hand side is a multiple of? It looks like it's a multiple of x. But maybe m divides x. And so maybe it's not a multiple of x. So I don't see that I can get a contradiction from this, unfortunately. It's not a bad thing to try. And you try something, if it works, great. If it doesn't, you have to try something else. So I need to get an x times y. I have ax plus by plus bp equals 1. How can I get an xy from that? What could I do? Thoughts? Multiply by y. So we'll call this equation number 1. So multiply equation number 1 by y, and that gives you now axy plus bpy equals 1. And now we use what was mentioned earlier. As p divides xy, we have xy equals mp. So we get amp plus bpy equals 1, or am plus byp equals 1. So we have two integers that multiply to 1, and one of them is greater than 1. Can that happen? Oh, I'm sorry. The left-hand side is not 1. What is the left-hand side when I multiply by y? It's y. So now we factored y. And so we see p divides y as claimed. And that finishes the proof. So the idea here was, we started with Euclidean algorithm. And what does it mean to have the Euclidean algorithm? Well, we've got x, y, and we have p. We know p divides x, y. We can assume p doesn't divide x, because if it divided x, we're done. So now we have 3 numbers to choose from, x, y, and p. Hope that we use the Euclidean algorithm choosing 2 out of x, y, and p. So it's either x and y, x and p, or y and p. Probably want p involved in it. And so that moves us down to either x and p or y and p. And when we try to use the Euclidean algorithm, we get the GCD of x and p or the GCD of y and p. We don't know what the GCD of y and p is, but we do know the GCD of x and p is 1 because p doesn't divide x. And so from this, we then were able to get that p has to divide y. And then we'll end today with the following. So I think we've seen this before. A field is a commutative ring with the property that every non-zero element of R has a multiplicative inverse. So unless your ring is just the element 0 and 1 equals 0, there's no way 0 is going to have a multiplicative inverse. So in any legitimate ring that we're looking at, 0 is not going to be invertible. So if you require that you have multiplicative inverses, that's too much to ask for. So the hope is that if I give you something that's not 0, it will have a multiplicative inverse. We know this is not true for some of the clock rings. And when we look at the clock with 12 hours, 2, 3, 4, 6, these are not invertible. And so a field is a commutative ring where every non-zero element has a multiplicative inverse. So if we look at these clock groups, Z mod, MZ, sus, so these are going to be the invertible elements. The star means the invertible elements in the ring Z mod, MZ. So if M is 12, Z mod 12Z would be the numbers or the equivalence classes from 0 to 11. And then we would look at the invertible. So for example, Z mod 12Z star is our old friend 1, 5, 7, and 11. And all of those will be invertible. So we're looking at all A mod M that are relatively prime to M. So we lose the evens, the 2, 4, 6, 8, and 10. We lose the multiples of 3, 3, 6, 9. But everything else survives. So we just have the set 1, 5, 7, and 11. In particular, if P is a prime number, then Z mod PZ is a field, often denoted by FP. So that means everything is invertible. Okay? So I will leave the first part of proposition 3.20 to you. So prove that the invertible elements are just the elements that are relatively prime. If P is a prime number, that's a special case. Then it's a field, which means everything is invertible. So for the second part, we have, 1, 2, 3, ... P minus 1. We're claiming that all of those are invertible. So proof. Let's say X is in 1, 2, ... P minus 1. So what's the GCD of X in our prime P? It's 1. So by the Euclidean algorithm, there exists A and B such that AX plus BP equals 1. So what is AX congruent to mod P? If AX plus BP equals 1, what is AX congruent to mod P? So what is AX congruent to mod P? So we have AX plus BP equals 1, or AX equals 1 minus BP. So when we look at things mod P, what is 1 minus B times P congruent to mod P? So we're just looking at the right-hand side mod P. So what is 1 minus BP congruent to mod P? 1. Right? So X is invertible with inverse equal to A. So not only does the Euclidean algorithm tell you that it's invertible, it actually helps you find the inverse. So this was the special case when M was a prime number. And the key thing that we used was the GCD was 1. Over here, we're saying, look at all the elements whose GCD is 1. Those are all invertible. And the claim is if the GCD is not 1, then they're not invertible. So you should be able to write that up. If you cannot write this up easily, please let me know. I have to go based on stares of people as to how well the information is being processed. And so if you are able to process this easily, if you can write this up easily, that's great. If you have trouble right now doing this, then you have to let me know. And almost surely if you are having trouble, you are not the only one having trouble. But you should be able to prove that if I look at Z mod MZ star, if A and M are not relatively prime, it's not invertible. If A and M are relatively prime, then it is invertible. We did the special case when M was a prime. You should be able to handle the general case. All right, so this is a good place to stop. So we will stop.